Hello, friends, and welcome to our third and final installment of Global Hack Week Security Machine Learning. I am super pumped to have you all back, and I'm looking forward to it. We are right on time, and so I will just stall for a few minutes because it feels wrong to really kick off the stream actually at 6 p.m. So we'll just kind of hang out for a few minutes. But I will let you know what we're in for. We are going to continue, of course, with our project for detecting credit card fraud. And actually, this is a great call out. So this is part 3 in a 3-part track. And so if you either are not familiar with Python or are not familiar with machine learning in Python, I would really recommend you go back and watch those streams because they will help you get here. But the good news is there's still time to sort of do everything. You are not limited in sort of the amount you can participate in this stream. So yeah, if you didn't get a chance to see those, go back, check them out, and then come and hang out with us here. We are going to reveal a little bit more drama. If you have been monitoring the Kaggle competition, you may actually know what some of this drama is about, which I guess I will drop a link there. We'll drop all our links. That'll be good. Okay. Here is our link to our Kaggle competition. And then where is a doc full of links? There we go. And here is our link to check in. Boom. Also, let me know in the chat if you have any other questions about stuff that's happened so far, and we can dig into that. Otherwise, let's see. Let me know what the weather is like where you are. I'm in Seattle, and the weather is very, very nice. It is very warm, and it is very sunny, and it's a good time. It honestly is making me want to be outside, which I will probably do after this stream. Juicy says, Vancouver, hot. Oh, is SkyCloud also in Vancouver or also at a place that is hot? This is very exciting. I'm going to Vancouver this weekend with my boyfriend. We're going on a very short trip. So actually, this is great to get the TLDR on what Vancouver's like. Actually, okay, this is what I need. Folks from Vancouver, given that we have a couple of you here, I've been to Vancouver a couple times, right? Because I'm just over the border in Seattle. But what are your like top picks in Vancouver? What should we definitely do while we're in Vancouver? Because I've been before, but my boyfriend has never gone. So we are definitely looking to fill up the weekend. Let's see, Waterloo, terrible air quality. I'm sorry to hear that. That's a bummer. I have not really spent time in Waterloo. I have driven through, but that's as close as I've gotten. Fremont. Wait, is this Fremont Seattle or Fremont, California? I'm guessing it's California because there's a neighborhood in Seattle called Fremont, which I'm guessing is probably not you. But if so, that could be cool. We could have a Global Hack Week coffee meetup. Okay, California. That's unfortunate. But I'm sure it's lovely and very, very hot. Stanley Park. Okay, yes, we'll add Stanley Park to the must-see list for sure. Canada Place. I am not familiar with Canada Place. Oh, is it like a large what's the word? Like pier kind of thing? Iconic landmark. Interesting. Convention center. Good deal. Ramen Danbo. Okay, we'll add that to the list. Ramen Danbo. I will have to give a report next time at Global Hack Week on how the trip went. The wait is 2 hours. Well, you know what? We got time, and I like hanging out with him, so maybe we'll make it happen. Okay, cool. So I am not seeing any questions materialize in the chat, which is great. Everybody knows what's going on, which I guess means we can just sort of recap and get into it. So I dropped that link to. I guess we'll do a very, very quick sort of recap of what's going on here. So we are doing this competition in Kaggle, on Kaggle, to detect credit card fraud. If you go to that link, you can come over here and click on code, and you can see all of the code that we have. So all of the ones with my little icon on it here. Oh, not that, but all these ones are the code that I have sort of shared for you to play around with. We've also gotten lots of community contributions, which is incredible. Looks like we have 4 notebooks shared by folks. And you can go and look at all of these, but we will mostly be looking at part 4, and we might venture into a part 5 notebook today. So if you are following along, you can go to the code section here, and then you can click on part 4, powering up our model, and you can click copy and edit, and you should be sort of in with me, and you can have the code that I'm starting from, so you can follow along if you'd like to. Okay, so I guess we'll get the big drama out of the way. The big drama, friends, is that, and actually, we can tell the story by looking at, oh, we got a comment. I don't know if I saw this comment. Oh, Thomas, thank you. So if we go back to our competition, actually, under discussion, I think 2 people shared similar thoughts. So Thomas's comment was good. As we saw last time, a lot of our also, if you are like I missed last time, or I've only seen one of the sessions and I have questions, let me know, like, hey Will, what are you talking about, in the comments, but otherwise we'll just kind of keep going. But so Thomas shared this sentiment of because making sure that we label fraud is weighted so heavily, the best strategy right now to get a high score ends up being labeling most things as fraud, right? So if we actually jump into our powering up our model notebook, so we can review a little bit. We did cross-validation, so that's, remember, splitting our training set into 2 different parts. So we can have sort of a training set that we know the answers to, but also a test set that we know the answers to. And so we can know how well our model generalizes. So this was us splitting it up. So we end up with like 13,000 and 4,000 in our 2 little sets. You generally want your validation test set to be smaller because you don't, you just need to know how well it does. You don't really need to have that much data in there. Then we split things up. And so our original problem, let's see. Our original problem on this, so our F beta score was with beta 0.5. The thing that we noticed is if we just by taking the mean of our predictions, we can see what percentage is labeled fraud and not fraud. So here, we're just telling our model to balance things, right? We say class weight balanced. And that kind of makes sense that we end up with about 50-50%, right? But here, our F beta score was 0.24. And something else that we learned that we could do, which I guess we'll use in another model. So we have decision trees that I think helped us do a little bit better with the F beta score. Okay, yeah, you can see 0.29. That's an improvement. But then one of the things we realized is if instead of just saying balanced, if we gave some weights to, if we said, oh, the weight for fraud is like 100, and then the weight for not fraud is 1, we're like really telling our model, hey, be sure you label a lot of things fraud, right? And if we do that, then we can get a higher score, right? 0.32 is higher. But if we look at our predictions and we just take the mean of them, we can see we're labeling 99% of our things as fraud. And this is like currently kind of the way that people have gotten high scores, is just kind of by calling almost everything fraud, right? But it's still not a very high score. It just is like currently one of the better solutions, is just to say most things are fraud. Hi, Kaka Prague. It's good to see you as well. Or it's good to see you, I guess. So this was a problem that Thomas called out. I believe if we go back to discussions, LF Santos said essentially a similar thing. And LF Santos actually proposed a solution, which was to say, what if we went back to F1 score and multiplied it by 100? So like new scores are better. And I responded to this and basically said, well, you can't, with the metrics in Kaggle, you can't just multiply by 100 arbitrarily. But there is a new metric that I think is going to work better for us. So the new metric is called F1 macro. And we'll pop into talking head. The way that I would describe F1 macro is, so we were looking at F scores, right? And you can change that value, lower or higher. But it's always from the perspective of your positive class, right? So for us, our positive class was fraud, right? And so you care about precision of fraud and recall of fraud, but it's all about fraud, right? And we don't actually care how well you classify non-fraud, right? And this is kind of one of the things that's leading to our problem here, is that we kind of ignore non-fraud. It still gets taken into consideration with precision a little bit, but not that much. And so the thing that F1 macro does is it says, well, what if we considered not just your positive class, but what if we also considered your negative class? And so what if we said, take your F score of your positive class, but then also take your F score of your negative class and average those together. And that's what F1 macro is. So this is what we switched to. And the goal here is that you have to make good predictions, not just getting if it's fraud right, but you also really have to get it good if it's not fraud, right? So that is our new score, and that is something we can take a look at in our notebook here. So if we scroll back up to our very top, next to F beta score, we'll import F1 score. And let's go and look at all of our scores, but as F1, and instead of beta equals 0.5, we will say average equals macro. So this is saying, hey, average across both of these classes and see how well you do. So we can run this again. And okay, so suddenly our original solution with balanced classes actually does quite a bit better, right? We got 0.38. So this is now a better score than currently anybody has on the leaderboard. So just by submitting those predictions, you could get a decent score. So there's another little treat for you. But we can look at our predictions should still be the same. This is about 50-50, right? But surely we can do better than that, because this is saying, hey, you submit a transaction, I'm going to flip a coin, and if it's heads, I'm telling you it's fraud, right? Half the time it's fraud. That's too much. So let's go down to our decision tree example. So this is with class weighted 100 to 1, right? We're saying, hey, model, you should care about fraud 100 times more than you care about not fraud. We can make our predictions again. Oh, that's an interesting decision tree it spat out. And so again, we'll say F1 score and average equals macro. And so here, this is still a little small, isn't it? Let me know if I need to make it even bigger. Maybe that's big enough. So here, our F1 macro score is even lower. This is really low. It's 0.081. And before, this was doing great, right? Under our F beta macro metric, it was doing great. And now with F1 macro, it's getting knocked down all the way to 0.08. And this is with predicting almost everything is fraud, right? And this makes sense because F1 macro is more balanced, and it says, hey, you have to care about the fraud, but you also have to care about the non-fraud. And so if you're saying everything is fraud, you're not going to do very well. So one thing we can play with is this class weight here. But before we get too deep into it, I want to jump back down to not just decision trees, but random forests. So a quick recap, remember a decision tree, this is basically a decision tree where it asks a set of sort of successive questions, right? It says, well, is this true? Okay, if so, I'm going to do that. Well, is that true? Okay, I'm going to go down here. And you end up with predictions after it asks a bunch of questions. Oh, Adam, I'm so touched that you came to say hello before you go to bed. Sweet dreams, bud, sweet dreams. So that's a decision tree. But a random forest says, what if we got a bunch of decision trees together and we had them all specialize in different things? and then we brought them together and made them vote. And so this sort of voting at the very end is how a random forest can outperform decision trees sometimes. And we did some science trying to pick the ideal depth and the ideal size. And one of the things that we saw was that a bigger tree will always do better on data it's already seen. Okay, I will put, actually, no, you're the first person to have asked, Adam. So I will put on the flower crown for you. Yeah, flower crowns are like a Global Hack Week thing for me. So whenever anybody asks for a flower crown, I whip it out. Excuse me. So we saw that that a bigger tree is always better on data that you've already seen, but it's not necessarily better on data you haven't seen before, right? Because the bigger and deeper you make it, the more likely it is your tree is just kind of memorizing specific cases and not learning anything general. So we played around with that. I guess that was still a decision tree, but random forests, we did a similar thing, playing around with the size. But I want to come back to a random forest here. So let's look at just our initial random forest code. So here we were doing our class weight 100 to 1, and we can do f-score 1 macro. So here you can see, again, we're not doing particularly well. And the reason is probably pretty obvious. We're calling almost everything fraud. And that makes sense because our weights are 100 to 1, right? So what if we tried lowering our weight? What if we just said 50 to 1? How does that affect our score? Okay, not really at all. And okay, yeah, we're still calling most things fraud. Okay, what if it was 10 to 1? Okay, suddenly that's a lot better. We're calling about 22% of things fraud, and we get a score of 0.48. Okay, well, what if we weight them evenly? And that's still pretty high, but we are, okay, yeah, in this scenario, we're actually only, we're not calling anything fraud, and we're already getting 47%, or a 47 score. So there's somewhere between weighting evenly and weighting 100 to 1 that is perhaps where we're going to get our biggest score here, right? So one thing I want to try is, what if we wrote a loop? So for, let's say, for fraud weight in, and we can have a list of, we'll say one. What if we said range 1 to 20? And so we're going to, for every step in this list, or in this loop, we're going to create a new random forest classifier. And we can keep our parameters the same, but the thing we're going to change is we're going to say that this weight is going to be fraud weight to 1. So we'll try 1 to 1, 2 to 1, 3 to 1, 4 to 1, 5 to 1, all the way up to 20 to 1. And we're going to see what score we make. So we will then train that random forest. I'm just kind of copying and pasting some code down. And then we can get our score. And so we can say scores. So we're keeping a running list of scores here. And when this is done, actually plot them. I'm going to say import matplotlib.pyplot as plt. And then we can say plt plot scores. Okay, cool. This is super cool to me. So you can see for a lot of different weights, we are basically, I mean, my guess is all of these are basically saying, what if we said everything is fraud, or what if we said nothing is fraud, right? And then as we introduce, as our weights get to the point where we're actually saying, well, what if a few things are not fraud, right? What if, what if a few things are fraud? If we adjust our weight such that we're saying, no, like make sure there's a little bit of fraud, make sure you catch some fraud, then our score gets better, and then quickly our score gets very, very bad. But so we can look in here, this range, it's kind of between, it looks like it's between like 7 and 10, right? And so this is a really common thing when you're doing machine learning, like science and machine learning engineering, is there's some parameter you're trying to tune and you're not exactly sure what number it should be. And so you'll start by just looking at a broad range of numbers here, but then you're going to want to rerun this and look at these numbers closely, right? So what if we reran this experiment? We can keep this, and maybe we'll be good scientists and say title, let's see, fraud weight versus F1 macro score. Okay, cool. We have that little graph there. And then I'm going to copy this down, and we're going to rerun this experiment with more finely grained numbers. Now, if I recall correctly, you can't do fractions in a range call. So we could import NumPy as NP. Here, let me just make sure I can create the proper range. So I think it's np.arange. You could say, oh, here we go, start, stop, and step. So we could go, excuse me. We could go from 7 to 10. We could increase by 0.25 every time. Okay, cool. This looks right. We go 7, 7.25, 7.5, and so on and so forth. So this will be our weights now. We'll call this fraud weights. And we can run the same experiment just on a more fine-grained set of weights. Also, because this experiment might take a little bit longer, I'm going to show you one of my favorite libraries in Python is called TQDM. TQDM. And what you can do is when you're looping over a list, you can wrap it in, say from TQDM, import TQDM. You can wrap it in this call to TQDM, and it gives you a very cute little loading screen or a little loading animation as you're running. Okay, so that actually went pretty fast, but you can see for sometimes you're running code that will take hours and hours. Having that little bar that shows you your progress can be really, really nice. Okay, so now we have new scores. And instead of just plotting scores, we can plot our scores versus our fraud weights because they're not linear. And let's see what we got. Oh, this doesn't look quite right. This isn't exactly what I expected. Although maybe it is. I mean, maybe it's a sign that we just need to oh, honestly, what it really is a sign we need to do is we need to set a random seed. What we said, random, is it random state? Okay, yeah, random state. So this lets it be a little bit less random for us. But maybe we also need to go further out. Maybe we need to count all the way up to 12. Okay, there we go. So this makes a lot of sense. If you're looking at this right here, if we scroll up, this graph is really zooming in right here on this little interesting peak here, right? There's this point after which changing the weight doesn't actually help us anymore. And that point seems to be right about here. And this does really seem like it's just shy of 10. So 10 would probably be a pretty good value. 9 would be a decent value. But something like 9.8 seems like a really decent option. So given that we have done some science now and we have a result, we could, for our final... and honestly, I'm not really that interested in forest sizes anymore. Boom. But so for our final, we could pick that value of 9.8 for our weights. And so come back up here, copy this down. I guess we can add a little note. Let's write some markdown. We can say weight, let's see, a fraud weight of around 9.8 seems to give us the best performance. So we can now say our weight is 9.8 to 1. And let's see how we do, at least on our split here. So we're ideally hoping to get better than better than 47 or 0.47. Oh, I'm scrolling everywhere. So we can train our model, and now let's test it. And okay, we got 0.5. That is a pretty good score, at least so far, right? And one way you could think about this is that if you are getting higher than 0.5, then that means you are actually solving, at least a little bit, solving both pieces of the puzzle, right? You're really solving the non-fraud question at the same time that you're kind of solving the fraud question. So we just ran a little experiment where we're trying to pick the ideal class weights. Does anybody have any questions about that? Any confusion or any interest in the weight? Why is this weight working? I would say an interesting thing here, and probably someone has written a paper on this, but our weights probably 9.8 probably get us back to being about balanced, right? It might be a little bit different, but it seems as though in our original data, it seems like we had about 9. We actually pretty much did have about 9 cases of not fraud for every case of fraud. And so this is really just kind of undoing that imbalance. And that seems to be the thing that gets us the best result. So why don't we why don't we actually import our test DF and generate some predictions? And why do we actually, I guess the important thing is, let's see how many of our predictions are fraud. Okay, this is great. This is, I think, really, really good news that our predictions here end up being really, really close to that original rate of fraud. Trisha says, my plots are coming empty, but the numbers are coming correctly. So let's see. If you're just seeing this box with no data in it, make sure that you're passing both your X values and your Y values here. I'm trying to think of what could be causing that. Here, one thing I can do right now is I can just publish a new version of the notebook. So right now you should be able to get access to it. It'll actually run before it publishes. Okay, it'll take a second. But at least this right now is working for me. So let me know if you can have issues, or if you're able to, once this finishes publishing, if you're able to grab that. Okay, so the number or the percentage of things we predict as fraud is really, really close to the original percentage of things that actually are fraud, right? About 10% of things. So this is a good point, is if you're in Kaggle, it should be fine. It should auto format for you. But if you are doing this somewhere else, for example, in a terminal or something, then running PLT show does give you, should actually make it pop out. But I imagine you're probably just running in here, which it should just work. Okay, cool. So I think we should try submitting this and see how we do. I guess a good moment to check back in on the leaderboard. So it looks like a lot of people submitted sort of the best solution that we had kind of done together. But clap did a little bit better. They probably got 2 or 3 things correct. So well done, clap. Okay, Skull Crusher for Life asked this question. The 0.5019 means what? Your prediction for something being fraud is correct 50% of the time. So this is a great question. And the answer is that it doesn't have a super simple answer. So really, there are 4 things that go into this score. And the 4 things are precision and recall, precision for fraud, recall for fraud, and then also precision for not fraud and recall for not fraud. So if you remember, I'd say the place that I would point you to is, not here. under code, part 2.5. Because I think this is a great question, because the metric here is like, it's one of those chunkier metrics, right? Like on some level of competitions where the metric is just accuracy, it's like, okay, that's easy to understand. But the metric here is a little bit complex. But so remember, precision is the idea of how many of the things that you said were important really were. So in this case, it's okay, how many cases that you said were fraud really were fraud. Recall, on the other hand, is out of all the cases that actually were fraud, how many did you correctly identify? How many did you say, oh yeah, that's fraud, right? And so normally F-score is just looking at that for the positive class. So that would be just considering fraud. But what F1 macro does is it says, well, let's take a look at it for the positive class and for the negative class. And so it's basically the question, out of all of the things that you marked fraud, how many really were? Out of all the things that really were fraud, how many did you mark? And then it also goes on to ask, out of all of the things that weren't fraud, how many did you mark as not fraud? And out of all of the things that you marked as not fraud, how many weren't fraud? So that's like 4 different things that it counts up, and all of those kind of get averaged together. Not exactly, but basically they get averaged together here. So one way of thinking about this is that even if you really messed up one side of the equation, say you didn't really do well at classifying fraud, but if you classified not fraud perfectly, then you could get sort of half of that, the precision and recall for not fraud, really high. But you couldn't get it above 0.5, right? And then the other side is, what if we were really good at classifying fraud and we got good precision and recall on that class, but we did really bad at classifying not fraud? And that also would be, you could get up to 0.5, but you couldn't get over. And so the thing that I would call attention to, okay, it's complete. We can check the leaderboard. Is, okay, well, this is a little bit of a bummer because the score ends up being a little bit smaller. Oh, Trish, I'm so glad to hear that it's working for you. I will say Kaggle. So I really like the Kaggle platform, and it's really cool. They give all this, all these compute cycles away for free. The catch is the environment can be a little bit shaky, and sometimes just rerunning something can be the fix. I have hit that a couple of times. So our score 0.48. That means we are almost to that point where we're fundamentally solving both halves of the equation, right? I'd say in general, if you get an F-score sort of above 0.5, that starts to mean like you've really solved something. It's not perfect, but you've really started to get something correct. And that is still better than all the submissions up right now. Which honestly, I apologize to Clap because they clearly worked at it and figured something out. And I mean, I'm sure if they rerun their submission, and they rebalance things, they should be able to get a good result. But right now, if you just copy my code and submit it, you can get 0.48. Yeah, I say the formatting around submission.csv. It's when I was in college, I did a lot of Kaggle competitions for like a club, and this was the biggest thing. Is like everybody's submission was just a little bit off, or it wasn't in the quite right order, or something about the formatting. But I appreciate that it is working for you now. Okay, cool. So I think I'm gonna leave. I think I want to leave. Decision trees there. Decision trees, random forests, very cool, very powerful, and specifically very easy to interpret, right? A decision tree up here, I think this is one of the big things I'd leave, is that if you need a model that you can understand what it's actually doing, then a decision tree is a great option. And sometimes it will surprise you. Sometimes it will look a little bit confusing. Which here, let's weight this actually down to our magic 9.8. Oh, that's interesting. Yeah. But so decision trees are just really interpretable, and that's a reason to go with them. Okay, but so it's been long enough that we have not actually used an artificial neural network. That's sort of the the elephant in the room. Everybody always wants to know, well, hey, couldn't you just throw an artificial neural network at this thing? And the answer is we absolutely could. And let's see how it does. But before we do that, we have to learn about one specific problem. So far, we have been using the class weight, which is basically telling the model how much to care about getting something wrong, right? But with an artificial neural network, you can go and write your own special loss function, but then you end up having to do sort of like a lot of math, and you really have to get into the weeds. And what can often be simpler is to, instead of trying to balance the model, just rebalance your data set. And so we're going to look at something called SMOTE. So the idea behind SMOTE. So SMOTE, now I have to actually look up the acronym. SMOTE, let's see. It is synthetic, I think it's synthetic minority. Oh, come on. What's the acronym? Synthetic minority oversampling technique. That is SMOTE. And so the idea behind SMOTE is, say you have an imbalanced data set like we have, right? We have a lot of cases of not fraud and only a few cases of fraud, right? And if you just hand this to an artificial neural network, it's going to do what all of our other models have done. And it's going to say, I see a lot of non-fraud. Maybe I should just say nothing is fraud, right? Like maybe that's a really good strategy I can learn. And that, of course, is not going to help us very much, right? So what SMOTE says is, okay, we need a couple extra examples of what fraud looks like. But I don't just want to like copy and paste, right? I ideally would have things that don't look identical, because if you just have a bunch of identical data, there's this chance that your model will sort of over-index on, it'll overfit and just say, well, whenever I see exactly this one row, I'll say it's fraud or whatever. And so what SMOTE does is it says, okay, you have this data set that is imbalanced. What if I try to generate some new examples that look really, really similar to the existing samples that you don't have enough of, right? So what SMOTE's going to do is it's going to say, well, can I create a couple examples of fraud that look really, really simple or really, really similar to fraud? Oh, yes, Con HQ, absolutely. A recording of this will be shared. In fact, you can find part 1 and part 2 in the Twitch backlog. So if you are catching up, you are more than welcome to go and find those. But yes, a full recording of this will end up on our Twitch after we finish, which honestly will probably not be that long. Conquer Prague threw out a great link. I think as I was preparing for this track, I think this is one that I came across and definitely would recommend. So without further ado, I'll say this this notebook is a little bit of a rough cut. I'll try to clean it up before I actually publish it. So we're going to start by doing just the same old here, right? We can get in our, okay, come on. Session starting. We can import our training data. And then just like our other models, an MLP classifier stands for multi-layer perceptron, which is essentially a neural network. And we can import that from neural network. So I will bring this up here. Our training data is just the same. We can create a train test split again, actually. So I guess I'll just run this line of code. So we are splitting our data again up into a validation training and a validation test set. Oh my goodness, thank you for asking. No, I totally, boom. Yeah, it was incredible timing because I just started getting into the code. Okay, so this is not public yet, and I will try to clean it up before I actually publish it. But we'll walk through most of the same stuff. So instead of a logistic regression model, we'll import a multi-layer perceptron model. And then we will split our training data into 2 parts. We can define our input columns again. And then here is where we can actually create a multi-layer perceptron. And I included a lot of different things in here, but I'm going to actually clean it up for now. I'm going to add a random state just so things are repeatable. Actually, we don't even need that. It's fine. It's fine. And so we can train a classifier. I don't know if people want to go deeper into like what's going on inside a neural network. Actually, this is pretty cool. because we already learned about logistic regression, ultimately, the idea of an artificial neural network is taking a bunch of neurons together, where a neuron takes a bunch of inputs and either it fires or it doesn't fire. It ends up being basically a 1 or a 0, right? So it spits out, it either says I'm activated or I'm not. And then that feeds into a bunch of other neurons, right? And you can add a bunch of layers in your neural network. But what are those individual neurons? Well, on some level, and this is, people invent all sorts of different things to go into their neural networks. But the simplest kind of neural network, each neuron is basically a logistic regression classifier. So on some level, what we're doing with an artificial neural network is kind of the same thing that we did with random forests. We're taking a bunch of logistic regression classifiers and smashing them all together, and feeding the inputs of some into the outputs of others, to end up getting an answer. If that feels a little hand wavy to you, it's because it absolutely is. And if you have more questions about neural networks, I'm happy to field them. But we don't need to understand everything about them in order to use them, right? So we created our classifier. Here, we trained it on our training data, and now we can test it on our testing data. We get 0.477, which this is not bad, but this is not better than we were getting before, right? And one of the reasons is because, again, our predictions are all 0. It did that thing where it realized there's a lot of fraud out there. Maybe I can just do that, right? Or sorry, there's a lot of non-fraud out there. Maybe I can just do that. So how do we make this better? Interestingly enough, so you might say, hey, all of our other scikit-learn models have just had this parameter of class weights. Maybe multi-layer, or maybe our neural network has class weights. But interestingly, it does not. If you just I'm searching for class weight on this page, and there's no option to set class weights. Interestingly, this actually is an open bug, and people are actually working on adding that. So if you're interested in getting into open source software, go contribute to scikit-learn and give us some class weights on this model. But so we don't have that option right now. So what can we do? Well, we can try this smote thing. And I think I was playing around with it a little bit down here, and I'll pull this up. So I guess let's summarize what's going on, and then we can move on. Let's call this markdown. Okay, what's going on here? Our neural network has learned that there's a lot of non-fraud, and that it can get a decent score just by saying nothing is fraud. So let's start with smote. Okay, so the first thing I want to do is actually, let's grab our training DF, and let's get our fraud column and get value counts. Value counts is a super useful function in pandas, and it will tell you how many counts you have of each value, right? Shocking, I know. So here we have, 16,000 versus 1,000. But if you say normalize equals true, it'll give you percentages, which is kind of nice. Okay, so here we see 91% of our transactions are not fraud and 8% are fraud. So what we can do with smote is try to even that out. So I'm going to import smote, which, remember, smote is this idea of maybe we can generate some more examples of fraud that kind of look like fraud, but that are new samples we can add to our data set. And so now we can run this example of fitting and resampling. So it's going to fit and kind of learn, well, what does fraud look like? And then it's going to resample by generating some additional examples of fraud. So if we run this, we should now be able to look at our fraud, or maybe we can even can we do value counts? Boom. Okay, so this is awesome. And we should maybe even say normalize as well. So now we have 50% fraud and 50% not fraud. And we actually have more data now. So now that we have that, what if we came back up to our multi-layer perceptron classifier and we trained it on, which really, now that I'm thinking about it, we really should be resampling our, not all of our training data, but just our validation training data. So let's go and resample that way. Still get the same result here. So now we can just train it on our input columns and fraud, which is what we're trying to predict. So we should get a new classifier out of this, and then we should be able to test it in the same way. It's really taken a second to train. So to kind of recap on what we're doing here. So we're using a multi-layer perceptron, which is just another way of saying artificial neural network. We're using a neural network here, and we were showing it all of our data and having it try to learn about what's fraud and what's not, right? But originally there was so much non-fraud, or there was so little fraud that our artificial neural network was just saying, I'm never going to say it's fraud, right? Because it's usually not. And so why would I ever say it's fraud? Which kind of makes sense, but it also defeats the whole purpose of what we're doing here, right? So what we are using here is called SMOTE, and the point of SMOTE is to generate additional examples of our data that look like the minority class. So technically the data is fake, but it should have this property of sort of looking like the minority class and beefing it up so that there are more examples of it. Okay, so it looks like we trained. It hasn't converged, which is a little bit concerning. And our score is worse. Hey, look at that. Okay, so let's look at our validation predictions. And we're saying 31% of things are in fact fraud, which this actually might not surprise you because we are, of course, saying, what's the word? We're in our training data now saying, well, 50% of stuff is fraud, right? And so even though it should be learning what fraud is, it's also just learning, hey, fraud is really common, right? And so it's learning one thing that we like and one thing that we don't like. So how can we fix this? Well, one thing we could try to change is here, it looked like we had 50% fraud and 50% not fraud, right? In fact, something that will be helpful is just creating a data set again here. Let's say input calls. Let's actually call this rebalanced EF. And we can actually add the fraud column back to, we can say fraud equals rebalance equals fraud. So now, if we look at just our DF as a whole, you should see we have our fraud column over here, and we have a lot more things that are now actually considered fraud, right? And the quality of those things might not be great, but hopefully it should be good enough that it'll actually help us in our prediction task. But the sort of error we made is that we actually we made it perfectly balanced, right? And I'm curious, actually, smoke sklearn. Okay, so the question here is, can we specify the ratio? Let's see. It looks like it just is going to make it balanced, which is okay. We can balance it ourselves. Yeah, we can balance it ourselves. So yeah, it certainly is a twist, isn't it? So we have our DF now, and a lot of it's fraud and a lot of it's not. So what if we separated it out into two data frames, one that's just all fraud and then one that's no fraud? Dreaming Oddball asks, hello, where can I find this notebook? It is not public yet, but I will publish what I have right now just so you can grab it. So part 5, if you come over to our competition, which I'll post a link to, and you click on the code tab, it should in just a second pop up here as soon as it actually publishes. Which actually, now that I realize, actually, it's probably going to take a second to run. So it should be available in just a second. But thank you for asking. It's thinking about it. Which honestly, the training of the neural network actually took a long time, and so that'll have to finish again before it publishes. Yeah, no worries at all. But yeah, it should show up on this page as soon as it actually finishes. Oh, it looks like it finished. Okay, maybe we can check one more time. Do we have? No. Oh, maybe I didn't make it public actually. Share public. Boom. Okay. Last time I'm going to refresh. Okay, there we go. Down at the bottom here. Okay, fine. Let's throw a neural net at it. Okay, great. So what if we first separate out our data frame into just the fraud and then just the not fraud? Do you recommend working on a Kaggle notebook for this competition? I would, just for convenience. If you want to, you can do all your machine learning in your own computer, and then you can just upload your finished predictions. I will say, I think all the template code, it just is. I would say it just is very easy, right? If you have your own environment on your computer that you really, really like working in, then I would not tell you not to. But yeah, I would recommend it just because it's convenient. And there's nothing wrong with doing this, on your own laptop or in a virtual machine or anything like that. Okay, so we can first check what things are equal to fraud. And so this is basically going to filter out everything that's not fraud. So this would basically, we could call this our all fraud DF. Of course, now it's actually dawning on me. There's probably an sklearn functionality for this. Sklearn resampling, resample stratify. Arrays replace stratify. Really, we want to resample to like an arbitrary distribution. Stratify ratio. Yeah, maybe that's not going to help us that much. Okay, so we'll keep going. We'll keep going this way. So we could say this is our all fraud data frame. And then we could create another one that is no fraud data frame. And so now something that we can do is we can just decide what we want our ratio to be, right? So what if we said our all fraud data frame, what if we just grab the first, let's see, how big is it? It should be like 12,000 or 12,000. Okay, it's 12,000. What if we reduced it by half? What if we said sample and the fraction is 0.5? So we call this small all fraud. And then we can actually join this together with our no fraud DF. Oh, come on. There we go, finally. We can do this with PD concat. So concatenation works on data frames as well. You just got to do it like this. And then we can call this our new balanced. New balanced DF. And if we look here now at our value counts, we should see a different percentage. It shouldn't be 50-50. Oh, really, we want just fraud. And OK, yeah, now it's basically 2/3 fraud, or 2/3 non-fraud, 1/3 fraud. And so the hope is maybe this split gets us a little bit closer. Dream Oddball asked, did you talk about neural networks in part 2? We actually did not. This is the first day that we're really diving into neural networks. We looked at linear regression, which is kind of the building blocks, or logistic regression, which is kind of the building blocks of neural networks. And we also looked at decision trees. And decision trees are cool mostly just because you can look inside and see what they're doing. With an artificial neural network, you really have no clue what's going on inside, which is often kind of a problem. But for us, maybe it's not. Maybe it's not. So now let's train a new classifier, and we can use our new balanced data frame with our input columns, and then our new balanced data frame with fraud. Oh, none of are in the columns. Okay, let's take a look. What does new balanced data frame look like? Okay, yeah, we have all the things. What does our error say? None of index are in the columns. Input columns. Oh, let's make sure input columns is defined up here correctly. Oh, okay, so technically, like these should be the same names, but maybe it's upset that they're different. We could redefine columns to be these guys. No, same error, which honestly makes sense to me. Yes. So unfortunately, fraud. Oh, okay. This is actually the problem. Fraud's supposed to be a string. So unfortunately, if you join in the middle of this, I think technically you can't see. Actually, maybe that's not true. I was going to say technically you can't see the beginning until we finish, but all of this will be recorded on Twitch afterwards, and so you can see it there, or I think it's kept recorded on YouTube like forever. So you can grab your link to that if that's a thing that you were interested in. Okay, yeah. So the problem was fraud was a variable and not the string here. So now this should work for us. And it's taken a minute to actually train. It's really crunching, you know. I'll also say I actually have no hard guarantees that this will actually perform better than our random forests attempt. This might not actually be better, but we'll see. Okay, it looks like we maxed out there. We didn't actually finish, but we trained. And 0.47. Okay. And we're predicting like 0.2% of things are fraud. So this is maybe a sign that we should be predicting more things are fraud. That's kind of the signal it's sending me. And we could be methodical about this. We could look at, at different splits. One thing we could try. Yeah, so this is kind of telling me, hey, maybe we should be predicting more things are fraud. And so one strategy is here we were saying get rid of half of our fraud examples. But we could take that back up and we could say, actually keep even more. Let's say, yeah, keep 70% of our fraud examples. So now it's even closer to being balanced. Not exactly balanced, but it's a lot closer. And this will probably take a hot minute to train again. But that's machine learning, right? You like tweak a few parameters and you run your code and you see how it's doing. But it seems plausible. I mean, the thing that I will say is I'm sure that there is a way to sort of tweak this network just right to the point where it is, it is providing better predictions than our simple decision tree. But the juice just might not be worth the squeeze. But it's training. It's on YouTube as well. Just look under the live tab and not videos. That is good to know. All right, it looks like we're done training. Moment of truth. Hey, okay. So we are improving. This is progress, not perfection. And if we look at this, okay, yeah, now it's saying 6% of things are fraud, right? And so this is something we could play with. I mean, we could even do this sciencey thing where we wrap it in a loop, and we keep picking different fractions, right? So, in fact, why don't we give that a shot? What if we say for fraction in, we can say fractions equals 0. Why don't we say 0.6, 0.7, 0.8? Do we include 0.9? Sure, let's include 0.9. We can say for fraction in fractions, we'll sample differently. And then we will train based on that new sample. And then we can actually get our score. So I'm just cramming everything, all that code we just wrote into a loop so we can run it repeatedly. And we can keep track of our scores. And we can say score, append, score. Now, this will probably take a long time because every time it was taken, I want to say like about a minute. So we can import TQDM again. And we can wrap this in TQDM. Boom. And it'll show us a little output. Mush, I'm glad to hear that you think this is cool. I'm glad to hear the positivity, man. I am sure hoping that it would be powerful if we got a result that we actually got to use, right? Which it seems like we're within striking distance here. 0.49 on our validation set is not bad, and it sure seems like we ought to be able to do a little bit better. Oh my goodness, you are okay. F4I54L, gold star for you. No, we totally don't. So we use fraction here. We should be plopping it in there, but we are not. We're not actually doing it. Cool. So that's a disaster. Oh no, that's not what I wanted. Okay, cool. We've exited our loop. And in fact, maybe we actually try half values as well. Maybe we try 0.65, 0.75, and 0.85. And so, yeah, we're picking that new fraction to sample with. Faisal was taken. Okay, fair enough. Gotta get creative. I respect that. Another thing we can do is there's this parameter called max iterations. So ultimately, a neural network will run in a loop, right? It'll keep refreshing and it'll keep reviewing all of the questions that you've given it until it feels like it's doing well. Packerprog asked this great question about when do we know when we reach sort of good enough number. And yeah, this is good. And I guess there are two questions here. One is, how do we know what the right value is for the fraction? And then separately, there's this question of, well, how do we know, how does the neural network know when to stop training, right? And those are two different questions. If there's, I imagine you were thinking specifically of one of those, so let me know. And and I can answer, or we could answer just both. But for our fit phase here, there's a parameter called max iterations. Actually, let's double check LP classifier. It should be max iteration. Oh, max iter. I'm glad I checked. So that, by default, that's 200, which is basically saying it's going to run through all of its data 200 times. But we have a lot of data. Maybe it's okay if we just run through it 100 times, and that should speed it up a little bit. But maybe that'll actually be, oh, that should, I guess, go not in our fitting function, but in the actual model itself. Yeah, so this question about like, hey, we're picking. So you were talking about the like how does the neural network know when to finish? And so there's this idea of convergence. So the basic loop of a neural network is it's going to train on all of its training data. It's going to look at all of its training data. It's going to make predictions. It's going to compare all of its predictions to the right answers. And then it's going to see how badly it did to know if it needs to change, right? And it does this in a loop because it might learn a little bit the first time, and then it might go back again, and it might do a little bit better, and it might go back again, and it might do a little bit better still. But it keeps doing this loop, right? Up until either you have a max set on it, so we could say, hey, only do this loop 100 times. But it can also do this thing called early stopping, where if it sees, hey, for the past 3 rounds, I've been doing basically the same, right? I haven't really gotten better or worse. Then it can say, I have converged, right? So convergence basically means your performance doesn't change anymore. And usually this is when you kind of get as good as you're going to get. And this is something that in most sort of like large neural networks, you will have some notion of, well, hey, if you're not actually improving yourself at all, like don't keep wasting GPU cycles, right? And so this is a thing we do. So it's either going to be it goes until you tell it to stop. So we say run for 100 iterations, or it'll go until it feels like it can't actually improve. And in this case, it kind of is still feeling at the very end like I still think things are changing a little bit. And so maybe we actually, I mean, another thing that you can do to try to get better performance is you can try to increase that. We could say instead of running for 200 iterations, run for 500 iterations or something like that. And it is, of course, just this trade-off of that's just more compute time, right? It's just more time. I mean, mostly it's more human time, right? Because we're just sitting here. But something that I would totally encourage is playing around with, well, what if I set max iters to a higher number? What if I set it to 1,000? And you'll be waiting for a while, but you might get sort of an interesting result there. Okay, so we are almost done. Because it's spitting out these error messages, our loading bar doesn't really look that good. But now that we have our scores and our fractions, we should be able to do our trusty dusty import matplotlib.pyplot as PLT. We should be able to plot fractions against scores. And what if we even said PLT style use ggplot just to make it pretty? And while we're making it pretty, let's give it a title. We can say fraction of data set that is fraud versus score. So Trish asks, it still didn't converge. Yeah. So we, in the course of our loop, we built 7 different models, and none of them technically converged. And sometimes that's because you have just a really tough problem that doesn't seem to have one solution. That happens sometimes. But you could imagine, hey, maybe if we just gave it more time, maybe it would have converged eventually. All right, moment of truth. Ooh, okay, this is super fun. So it looks like, so I don't know what's going on over here. This seems a little bit funky. But it looks like in general, if we just kind of zoom in over here, it looks like a value of using 70% of our fraud data set seems to do the best for us. So something we could try now is, now that we have a good parameter for this, what if we actually tried building one more model, but we gave that model more time to run? So we kind of did a short experiment on a lot of different models. And now that we have a model that we like, so we can grab, I guess we can really grab all of this. And I'm trying to be a better scientist with y'all. So let's add some more notes. It looks like our best outcome was with using 70% of the fraud data. Let's try building a model with that, but with even more iterations to see if we can improve. So now we will just pick the fraction. It looked like 0.7 did the best. But now for max iter, I mean, hey, we got time. What if we say 1,000? And what if we see if it finally converges at 1,000? And I think all that should be good. Oh, y'all, my eyes have been so dry recently. You know what it is? I've been playing Tears of the Kingdom. Let me know in the chat if you are playing Tears of the Kingdom, because that's what I'm doing right now. I mean, not literally right now. It's really, it's work, it's streaming, and then it's Tears of the Kingdom. Those are the big three. Not really a lot of like eating food or like sleeping. If no one on stream is playing Tears of the Kingdom right now, I will be shook. Thomas is playing Tears of the Kingdom. There we go. Thomas, how far are you? Have you? I feel like this is always the question, because like I got in and I did one of the. They're not called divine beasts in this one, but they're basically divine beasts. I did the Rito and went over to the mountain, and then I just got sidetracked. And for the past week, I've just been like trying to upgrade clothing and stuff. So I technically have only finished one out of the three, but I'm curious how far along you've gotten. Okay, it looks like we finished, and it looks like we did in fact converge. So at some point it converged. Oh, Thomas is out here already done. Thomas done beat Ganon. Wait, okay, so this is my question. I thought it was the Demon King, Thomas. I thought in this one it's called the Demon King. I guess it's kind of like the Divine Beast. It's like, yeah, they're not the Divine Beasts. Okay, 0.483. So that's actually not that much better. Which there's an interesting thing that happens. Sometimes actually cutting your model off early actually helps you avoid overfitting, right? If you give it a lot of time to be learning, it can take some of that time to sort of learn the wrong lesson. So maybe we actually do want to cut it back down to 200. I'm curious to see if we just cut it back down to 200, because here it looked like, or even 100. What was it? 100? Or I guess we said, or yeah, I guess in our loop we said 100, because if we set it to 100 and the score is higher, maybe that's just what we want to go with. Yeah, so technically we have early stopping built in, but it only not early stopping. Yeah, we have stopping when it converges built in. But yeah, I think you're exactly right. I think that trying to cap it a little bit earlier could be powerful. Cool, we cut it off early. And so the question is this score better than 0.483? And it is in fact. So it seems like there was a sweet spot somewhere along there where we actually got better validation performance using, in fact, less compute. So on that note, I think maybe we submit this and we call it a day on this stream. We'll of course do a lot of wrap up, and I mean, y'all have still 2 more days to keep competing and keep experimenting. And I will hop back on Discord to let you know how everything turned out. But yeah, maybe we try submitting this. And one thing you can do is if you ran a long experiment, you can just comment it out, because now it won't run when we submit it, and it should submit faster, which is just generally a good idea. So we feel pretty good about running this at 100 iterations. And so we should be able to do now. In fact, I'll pop over to part 4. And we should be able to scroll down here to when we made our test predictions. And we should be able to reuse this code. I'd say once you generate one successful set of test predictions, It honestly is. All right, we don't want random forest. We really want classifier here. We got some predictions. And actually, I'm curious on our current predictions, what percentage of them are fraud? Okay, still 0.06, which is interesting. This is like it's a little bit conservative on assigning fraud, which I think is super interesting. And now we can just submit that and see how we do. Boom. All right, let's try submitting. Okay, do we have any other big questions? I guess I will reiterate. I feel like I do my little spiel about like, there are 5 ways to win. But there are, in fact, 5 ways to win a swag drop in this competition. And they are, 1, and while we're waiting for this, I can kind of walk through it. 1, being first or second on the leaderboard. Trisha, quick to the punch here, jumped up to 0.47. Love to see it. Clap, clap, and Thomas are close behind. But so first place and second place will both get swag dropped. The person who has the best, by my decision making, the best discussion, and I think we actually had a lot of really great, both some love for my dog Darwin, but also some really great like conversation about how the original metric felt a little bit broken, which I really appreciate those. There's also going to be a prize for the best code published, right? So it looks like right now we have 4 notebooks. And then I guess finally, I'll take everybody who's on the leaderboard and I will randomly select one person in a raffle. So just by submitting, you can get access to that. I guess the one thing I'll throw out is that on the leaderboard, there are now 33 people, which is incredible. It's so cool that so many folks have come in and submit. But there are only at this point 3 comments and 4 code submissions. So if you wanted to leave a comment or start a discussion or publish some code, that could be a way to get a swag drop. But also it's about the learning. It's not about the swag. But sometimes it kind of feels like it's about the swag. Okay, let's come back. Are we? Oh no, submission file not found. This is tragic. Oh, it failed. Okay, we have some error somewhere. Let's fix our error, why don't we? Fractions is not defined. Oh, that is unfortunate. Okay, where do we? Oh, it's probably in our graph. Yeah, okay. Our graph can't mention fractions either. It looks like, okay, all the instances of fractions are commented out now. So let's try submitting that again. Oh, the flashbacks. Wait, is this flashbacks to trying to debug errors, or is this flashback to other competitions? Tell me more. I'm interested in reliving your trauma. Oh, y'all. Oh yeah, yesterday. Yep. No, that's that'll do it to you. That'll do it to you. Let's see. Do you just need a Kaggle account to run Python notebooks in the competition, or do you have to link it to a Google account with a credit card on file? Running models can't be cheap. Yeah, so this is a great question, and I love talking about it because it is like it feels like a scam, right? Like in a good way. So the answer is you do not. There is actually no way for you to pay Kaggle. Kaggle does not have a premium account. They have no way of charging you, and you just get this for free, right? And on the one hand, it's like, okay, lots of platforms will give you a little bit of compute for free. Kaggle will give you 30 hours of GPU time per week for free. And so the amount of free compute you can get on Kaggle is kind of insane. And I think the sort of the understanding that they have is, hey, we want this community of really dedicated data scientists, because if we get that, then we know we're going to be able to solve really tough problems, right? Which I haven't really talked too much about Kaggle, but if you just go to Kaggle Home or whatever, I guess competitions, most of their competitions here are these sort of big, large scale problems, like, getting better at recognizing sign language or reports on AI, or this is like a really cool like history challenge where they're trying to get scans off of these scrolls they found in Mount Vesuvius. And so their understanding is like, hey, if we give a little bit of compute away for free, then we can build this community that can solve these really interesting problems, which is sort of the Kaggle thesis. But yeah, there's absolutely no way for you to pay Kaggle money, and so this is not a you are in some ways not their customer. You are helping them solve problems, right? That's sort of the way it works. Which people who want to run these competitions, they go and they find it. They give Kaggle lots of money, right? They say, hey, we want to solve this problem. Can we throw money at you and you put all of your data scientists on it? Oh my goodness, that's incredible. I appreciate that. I appreciate the determination, and it looks like you're near the top of the leaderboard. So hopefully it works out for you. But either way, I hope that you have a sense of fulfillment and accomplishment. Cool. So we did submit, and if we look at our leaderboard, 0.5, 0.5. That's better. We're improving. Huh. Trisha's still at the top of the leaderboard. We'd love to see it. So I know I said, oh yeah, the point in time where you kind of hit that greater than 0.5 on an F1 macro score, that's when you kind of know that you've kind of started to solve both parts of the problem, both the fraud and the not fraud. So I think on that note, I think we'll do our final recap here, and we will sign off. Okay. So this is actually, sorry, this is separate. I do want to respond to this. So click to open in Google Notebooks. Yeah. So if you want to, no, so this is a great point, and I won't backtrack because as long as you stay on Kaggle, it is all free. So what you can do if you want to play along is, so you can come to one of the notebooks here, and if you click on it, you should have a button that says like copy and edit, and you should be able to stay inside Kaggle. You can go, I think, over here. Yeah, you can open in Google Notebooks. And if you go here, this takes you to Google Cloud. And I mean, if you want like insane amounts of compute, then you can do that. But yeah, no, I would not recommend that for this. I mean, sure, go use Google Cloud. I support it, but no, you can do this for free. And yeah, that is weird that it was before you had a Kaggle account. But if you create a Kaggle account, you should be able to do exactly what I'm doing. And just come in here and see this kind of editor, and this is always and should always be free. Which I'm actually happy if you're going through it right now. I'm happy to stay on stream for a bit and field more sort of troubleshooting, because yeah, I definitely make it clear that you do not have to, and you really should not be paying any money to participate in this stream. Like sure, if you really wanted to, you could go and do that, but no, I want to make it very clear this is not. Yeah, I'm not going to walk through how you could spend money on this because I think this is it's for learning and it's for fun. But yeah, the free compute time is pretty crazy in a good way. Which if you actually want to use the GPU, you can come up here, and again they have that button that you can go to Google Cloud. Which so Kaggle is owned by Google, and so that is part of the. Hey, like people wanting to work on these serious problems, like maybe we can, we're giving them a lot of free compute, but maybe we could sell them some compute if they, if they want the biggest GPU or they want the GPU for more than 30 hours a week. But you can also just click here and you can pick an accelerator to use. So they have TPUs and then two NVIDIA GPUs. And so you can click on those and use them sort of in your code. Nothing that we've covered so far actually uses the GPU, so I actually wouldn't like there are ways that you can use them in this problem, but we have not really covered it. So I would not worry too much about that. On that note, I think we're about at time, and if we don't have any additional questions, I think I will whip out the kalimba one last time and I will sign off. But it has been an absolute joy hanging out with you this Global Hack Week. I guess I will, before I do that, drop the registration or the check-in link one last time. Boom. And we will say goodbye for now, I guess. But I will be back on Discord to announce everybody who won at the end there, probably on Saturday. Thanks, y'all. I'm so glad y'all were here, and happy Wednesday and happy hacking. And thank you for all the positive words here. Take care, y'all.